Good afternoon. So today we will continue with our next part of Unit 1, that is algorithms and the various different topics related to algorithms, and then along with that number theory. So in this part, Unit 1 part 1 consisted of propositional logic, equivalence, predicates, quantifiers, functions, sets. Okay. So that concludes the propositional logic part along with sets and functions. Now in this part we will study algorithms, which you already have a general idea about. Then the next thing is complexity of algorithms, integers and division, integers and algorithm, applications of number theory, and matrices. So this is part 2 of unit 1 only. Now the next thing is algorithms. So why do we need algorithms in discrete mathematics? There are many general classes of problems. So general classes of problems arise in discrete mathematics. For instance, the different problems that can be solved, or some applications are given given a number theory. If we want to make a message secret, then we need to use some kind of algorithm, and generating random numbers, assigning memory locations to computer files, internet security. So all of these are different applications of number theory along with algorithms. Okay. Now number theory is basically a very essential tool. So number theory along with algorithm, it is an essential tool for internet security and networks. Okay. So the next thing, where are we going to use algorithms? For instance, given a sequence of integers, finding the largest integer, or given a set, list all of its subsets, or else given a set of integers, put them in either increasing order or even in decreasing order. We need to define some steps. Given a network, find the shortest path between two vertices. So these are the various problems where we have to construct a model. So what we generally do is we construct a model. A model is constructed, and then we translate it into mathematical context. Okay, so this is translated into mathematical context. And we have already studied a few discrete structures which are sets and functions. We'll be studying sequences later, along with the other structures which are permutation, relation, graphs, trees, etc. Okay, these are the discrete structures which we will be using along with algorithms and number theory to perform or to solve the problems in discrete mathematics. Now, setting up appropriate mathematical model is only a part of the solution. So whenever we are speaking about setting up a appropriate mathematical model, so over here, to complete the solution, a method is needed. A method is needed, and this method will solve the general problem using mathematical model. So ideally, whenever we want to solve the general problem, we require a certain number of steps. A certain number of steps are required, and these are to be arranged in some sequence, and in some sequence arrangement should be done. So arrangement is to be done in some sequence. Okay, so that sequence of steps, this entire process which results in sequence of steps, is known as an algorithm. Okay, this sequence of step is known as an algorithm. Now let's see the methodology and the definition of algorithm. So first and foremost, construct a model that translates the problem into a mathematical context. Then build a model that will solve the general problem using the model. And we need a procedure that follows a sequence of steps that leads to the desired answer or to our solution. Such a sequence of steps is called an algorithm. Now, where did the term algorithm originate? It was by a mathematician known as Al-Khwarizmi. So that name has been corrupted or has been changed to get the term algorithm. Okay. Now, what is the definition of algorithm? An algorithm is a finite set of precise instructions. So why am I underlining this? I'll tell you in a moment. Is a finite set of precise instructions for performing a computation or for solving a problem. So these are few of the properties of algorithm. That is, the steps should be finite. Steps should be finite and also precise and give us the correct solution. So we'll study properties of algorithm in the next slide. But for now, that is, algorithm is finite. So if it is infinite, then it is not an algorithm, because we need to have some finite steps and then that should give some correct solution. Okay. Now we will see an example. Describe an algorithm for finding the largest value in a finite sequence of integers. So we have been given finite sequence of integers. What are the steps we will follow? First, and before that, let me give an example of the problem that we are about to solve. So over here, you already know how to find the maximum number in a given array. Okay, so this example that we were about to solve is this one, which you have already studied in C programming. So suppose if we have a list of numbers, then how do we start? We initialize the first element. So this is our first element, A1. Okay, generally in C we take A0, but here I am taking A1. It is okay. A2, A3, A4 and A5. Now over here, we take a temporary element max, which is initialized to A1. Okay, and we check by using a for loop. We check all the rest of the elements. So I is equal to 2 to I less than 5, I plus plus, or we have to take I less than 6, I plus plus. Then over here, we keep on checking whether max is less than AI. If max is less than AI, then we change max is equal to AI. And this is the end of the problem. So over here, if we check 45 with 60, in the first case, 45 is less than 60. So we change max to 60 at I is equal to 2. After that, I is equal to 3. Again, the comparison is done. 60 less than 21. The condition is false. So 60 is kept as it is. So over here also max is equal to 60. Then at I is equal to 4, we have 38. So max remains 60. And then at I is equal to 5, we have 2. So again, max will remain 60. So at the end, our maximum element will be 60. So this is how we find the maximum element in a finite sequence. Now let's see the solution for our problem. First and foremost, Set the temporary maximum equal to the first integer n in the sequence. So what was that? Max is equal to a1. Okay, we have seen it already. Then the next thing is compare the next integer in the sequence to the temporary maximum, and if it is larger than the temporary maximum, set the temporary maximum equal to this integer. So that this part is the for loop and the if statement. So this entire thing is this. Then repeat the previous steps if there are more integers in the sequence. So we have to keep repeating this. Then stop when there are no integers left in the sequence, and whatever maximum value is at this point is the largest integer in the sequence. Now, why did we write these steps? So you know this is not an algorithm. What is this then? This is a pseudocode. What do you mean by a pseudocode? Intermediate steps between an English language description of an algorithm and an implementation of this algorithm in a programming language. Okay, so this entire thing is known as a pseudocode. Now, after that, let's see the algorithm. So for the algorithm of finding maximum element, we take a procedure. The procedure name is max. And what is the input being given? The input is an array from a1 to an of what type? It is of the type integer. Okay, after that we initialize the first element to a temporary variable which is max. Then we keep comparing the elements from a2 to an. If max is less than that, then we initialize whatever element is greater than max to max, and at the end we get the maximum element. So we are mentioning max is the largest element. So over here, whenever we are writing algorithms in discrete mathematics, we have to start with procedure and the procedure name. This is input part and this is the output part. Okay, so and the rest of the procedure is written here. Then the next thing is properties of an algorithm. So there are generally several properties that algorithms usually are supposed to have, and whenever you are designing an algorithm, it is better that you keep these properties in mind while designing the algorithm, so that you get the algorithm which is finite and which gives the correct result. Let's see this. So the first property is about input. What do you require when you are taking an input? An algorithm has input values from a specified set. Okay, from a specified set you are supposed to give input to the algorithm. Then the next property is output. From each set of input values, an algorithm produces output values. So whenever you are giving input, the algorithm is supposed to produce an output, and the output values are the solution to the problem. The next is definiteness. The steps of an algorithm must be defined precisely. Precisely means correctly or accurately, so that there should not be any confusion when you are taking any of the steps of an algorithm. Then the next thing is correctness. An algorithm should produce the correct output. So when you're defining the steps precisely, it should produce the correct output values for each set of input values. Next is finiteness. An algorithm should produce the desired output after a finite, they may be large number of steps, but they should be finite. It never should be infinite. We should not write an infinite algorithm which is of no purpose. Effectiveness. It must be possible to perform each step of an algorithm exactly and in a finite amount of time. Okay. And the next last thing is generality. The procedure should be applicable for all problems of desired form. So whenever you are writing an algorithm, it should be applicable for all values of the set, not just for particular set of input values. Okay. Now, after this, we will see a few algorithms that you have already studied in your earlier subject, C programming. So we will see the same algorithms and we will see an example with each of them. So the first is searching algorithm. So what do you mean by a searching algorithm? Whenever the problem of locating an element in an ordered list occurs in many contexts. So for instance, if we want to search a word in a dictionary, So these kind of problems can be solved by searching algorithms, and the general searching algorithm is described as follows. So this is the formal definition of a searching algorithm. Locate an element X. So we are supposed to search element X in a list of distinct elements. So that means that every element in your set is different, A1, A2, AN, or determine that it is not in the list. So we have to search element X, and if that X is not there, then we have to inform that up also that we don't have the element X in the list. So we should provide as a solution to this search problem the location of the term in the list that equals X. So we have to give the solution, that is wherever that X is located, we have to provide the location. So with respect to the searching algorithms, we have two types of search. The first is the linear search or the sequential search. Linear search or sequential search, and the next is the binary search. So for linear search, first let's take an example. So to search for, we are trying to search X is 30. So we are trying to search the element 30 in the list. And what is our array? Array is of 20, 40, 10, 30, and 60. So since we are generally accustomed to using index 0, so we will start with index 0, 1, 2, 3, 4. What are the steps to be performed? The first step is step 1. Compare 30 with value at index 0. Okay, so 30 is compared with 20. Is it equal? No. So we move on. 30 is not equal to 20. So we move on to the next element in the index, which is 40. So let's do that. Again, compare 30 with value at index 1. Okay. So now 40, is it equal to 30? 40 is not equal to 30. So we are moving on to the next index value, which is 10. So the same way you can say 10 is also not equal to 30. We move to step 4. 30, we have found the key, which is 30 at index 3. So we are supposed to mention that the target is found at index 3. Okay. So this is the way we can write the, we can take an example now. Let's see the algorithm for the same. So linear search procedure, the name of the algorithm is linear search, so mention that. And what are the input? The input is the search element. So the input is the search element X along with an array of integers. And what are the integers? They are distinct. So any two integers in that array are not same. Next, we have to initialize the index value I is equal to 1. So normally, whenever we are seeing these problems, index value is being taken as 1. Now, while I is less than or equal to n, and we have not found our element, that is x, in the array, keep on incrementing I is equal to I plus 1. If I is less than or equal to n, then location is equal to I. Now what does this mean? So first and foremost, I is 1 and 1 is less than, if we have 5 elements, 1 less than 5. So I am taking the same problem that we have taken, which is what are the elements? 20, 40, 10, 30, 60, and x was 30. Now 1 is less than 5 and we check whether your 30 is equivalent to 20. No, it is not equal. We increment I to 2 and check whether I is still less than n, and we keep on repeating the loop. If we have found the, if this while loop condition becomes false, then we just mention that wherever your location is found. So in this case, since we are taking I is equal to 1, so index value starts at 1. So the location will be equivalent to 4 and we will end it. Suppose if we don't have 30 in our array, we instead of 30 we have 80. So and in that case we mention that location is equal to 0. Whenever we are mentioning location is equal to 0, that means our x is not found. So we mention that also. Location is the subscript of the term. Subscript means index of the term that equals x, or it is 0 if x is not found. Then the next thing is, the next search algorithm is binary search. So what is binary search? Binary search is a searching algorithm that can be used when the list has terms occurring in order of increasing order. So whenever they are listed from smallest to largest, we can use binary search, and this proceeds by comparing the element to be located to the middle term of the list. Okay, the list is then split into two other smaller lists and the procedure continues. So let's see, the constraint is that it can be used when the list has terms occurring in order of increasing size. So this is an important condition for binary search. Okay, the list has to be in increasing size, and the methodology is that compare the element to be located to the middle term of the list. So with respect to that, let's see an example. So the x value that we are supposed to search, x is equal to 7, and the array is 3, 6, 7, 11, 32, 33, and 63. Now, what will be the first step? The first step over here will be, we have to find out the middle element. So the middle element, total elements over here, let's begin our index with 1 again. So index is 1, 2, 3, 4, 5, 6, 7. So the middle element over here is 11. So step 1 will be, write your middle element, which is 11. Compare the search element with 11. So compare 7 with 11. Now 7 is less than the middle element. So search for the key on the side before the middle element. Now, so which side are we supposed to take? We are supposed to take this side. So then the next step, step 2 will be, our array is now only confined to 3, 6, 7. Again, what is the middle element? 6. So 7 is greater than 6. So we are supposed to search the array which is after the middle element or the right side. Okay, in that case, search for the key over here. In the case of step 3, we will see that key is equal to middle, and we mentioned that 7 is the third element in the array. Okay, so this can also be given by another example. So over here, search 19 in the list. We have an array of this sort. So what are we supposed to do? First and foremost, take the middle element. So over here, the middle element is, so we are splitting the array into two subsets and comparing 19 with the largest element of the first set, we see that 10 is less than 19, so we search the other part. In this way, we will continue until we find the element 19, which is the 14th element. Okay. So in the same way, we can write the algorithm. The procedure is binary search. The input is X, which is a search element along with the array, which are in increasing order. If there is some property about the input, you are supposed to mention it over here. Now, we take I and j. So for an array, I and j are the endpoints. So I will be the left side, the element which is at the left, the starting element, and j is the index for the last element. So we continue this search till when I is less than j. We find the middle element. So this, if you remember, is the floor value. That is, if we get 2.5, we are supposed to take as 2. So in this case, we once again verify by using a conditional statement if x is greater than am. Then we keep on incrementing until we get the location. The same thing we are using whenever we write location is equal to 0, it means the element is not found. Next we are taking the topic sorting. So sorting is basically putting the elements into a list in which the elements in the list are in increasing order. So basically sorting is ordering of elements. Ordering of elements. Sorting is putting these elements into a list in which the elements are supposed to be in increasing order. For example, when we are sorting the list 721459, we just put these numbers in increasing order. Similarly, for sorting of alphabets. So with respect to sorting, in this topic, we will study two sorting techniques. One is bubble sort and the other is insertion sort. So for bubble sort, it is one of the simplest sorting algorithms, but it is not efficient. It puts the list into increasing order by successively comparing adjacent elements. So what do you mean by that? Let's see this with an example. So over here, bubble sort, in the case of bubble sort, let's take an array 3, 2, 4, 1, 5. So in the beginning, first and foremost, that is the first pass, we will compare in the case of first pass, I'm mentioning it over here. So at the first case, we will write this list, and remember we have to sort it in increasing order. So that means the smallest element should be placed first. So we compare 3 and 2. With respect to 3 and 2, which is the smaller element? So 2 is smaller, so it goes up. So we have 2, 3, 4, 1, 5. Okay, we have replaced or swapped 3 and 2. After that, we check the next two elements 3 and 4. So these are in the correct order, so we keep it as it is. We are not swapping over here. The next pass, again we will write 2, 3, 4, 1, 5 and compare 4 and 1. Okay. Now over here 1 is the smaller element, so it goes up. So I'm circling the smaller elements. So over here you will get 2, 3, 1, 4, 5. We again compare 4 and 5, but 4 is the smaller element and it is placed correctly in its position. So we will end it. Now by this time we have compared the adjacent elements successively and we have reached the end of the list. But is our array sorted? No, it is not sorted. So we will continue with the second pass. In the second pass, again we will start from the first element. So we will write our list as it is 2, 3, 1, 4, 5. Now compare 2, 3. we don't require any swapping, we leave it as it is. Then the next thing is 2 3 1 4 5. Now we have to compare 3 1. We are supposed to do the swapping because 1 is the smaller element, so let's swap it. 2 1 3 4 5, and then compare 3 and 4. In the case of 3 and 4, we do not require any swapping since it is right now in its correct position. So it is left as it is, and then 5 is the last element and it is in its correct position, so let it be. Then in the third pass, we will write our list again. Start with the first two elements, 2 and 1. 1 is the smaller element, replace it, and we will be writing 1 2 3 4 5. Now over here we see that we have arranged 4 5 in the correct order, that is they are in its rightful position, so we will keep it as it is, and then we will go for the fourth pass. Compare 2 and 3 over here, they are in its correct position. 1 again we write, compare 1 2 finally, rightly placed, so this is the sorted array. Now let's see the algorithm for the same. So over here, the same example that I've taught, whenever you're taking ordered and permuted, so in this case, whenever we are swapping, I am showing that by an arrow, and whenever we are not swapping, it is simply mentioned. In the second pass, we understand that 5 is in its correct position, so we keep it as it is. In the third pass, when we compare 3 and 4 and they are not replaced, we understand that 4 is in its correct position. Similarly, we continue till we get the ordered list in increasing order. Let's see the algorithm. Procedure is bubble sort. For I is equal to 1 to n minus 1, that is, it calculates the number of passes. Why we are using two for loops? Because one is for the passes and the other is for the interchanging of the element if one is less than the another. Then the next one, insertion sort. In the case of insertion sort, it is a simple sorting algorithm, but not even this is not the most efficient. To sort a list with n elements, the insertion sort begins with the second element. So the insertion sort, what it does is, it compares the second element with the first element. So second element is compared with the first element, and inserts it before the first element if it is smaller than the first element, and after the first element if it is greater than the first element. And at this point, the first two elements are in the correct order. Then we compare the third element and this continues. So let's see an example first. So we are supposed to sort the array sort the array 5 1 6 2 4 3. So for this, we compare the first two elements and we see that the second element is smaller, so we insert 1 over here. Okay, so 1 5, 1 is less than 5, let's mention that. So 1 5 6 2 4 and 3. Next again we compare 6, the third element, with the first and the second element. 6 is greater than 1, 6 is greater than 5, so it is in the correct position. After that, in the next step, we will compare 2. So 2 is compared with 1, 2 is greater than 1. Then we compare 2 with 5, so 2 is less than 5. 2 is less than 6. So in this case, where are we supposed to insert 2? We are supposed to insert 2 before 5. So we will get 1, 2, 5, 6, 4, 3. And after this, we are supposed to compare the next element 4. So 4 is compared with 5, 1 and 2, which it is greater than, and 5 and 6, which it is smaller than. So it is rightly placed before 5. So here it will be 1, 2, 4, 5, 6, 3. Then the last element 3 is compared with all the elements. It is greater than 1 and 2 but smaller than 4, 5 and 6. So we place it before 4 in this way and the array is sorted. So this is your insertion sort. The same can be shown with the help of an algorithm in this way. So insertion sort, we take from the second element, compare it with the first element and keep swapping it. The next is greedy algorithm, which is basically an optimization problem. What do you mean by an optimization problem? Whenever we are using an optimization problem, the necessary requirement is that we are supposed to find a solution to the problem which is either minimizing or maximizing the value of some parameter. Suppose if we are finding the distance between two cities or a route between two small cities, then we are supposed to find the smallest distance or the minimum distance. So over here the distance is minimized, minimum distance. And similarly determine a way to encode messages. In this case, we are supposed to encode messages using the fewest bits. So even this is a minimization problem. And finding a set of fiber links between networks. So in this case also we are using the least amount of fiber. Apart from that, maximization problem will be, suppose if we are trying to, suppose a salesperson is trying to deliver packages. So he wants to deliver maximum number of packages in the least distance to be covered. So this can be known as a maximization problem. So greedy algorithm, what it does is, it selects the best choice. Greedy algorithm selects the best choice at each step. Instead of considering all sequence of steps. So greedy algorithm, instead of considering all sequence of steps, it considers the best choice, and this may not result in this type of problem. It may not result in optimal solution every time. Sometimes it may give you an optimal solution, but sometimes it may not give you an optimal solution. So algorithms whichever make the best choice at each step are called as greedy algorithms. So let's see the topic. Problem statements. So we have over here the change making problem. So in this case, what we are doing is we are considering a problem of making n cents change with quarters, dimes, nickels and pennies, and using the least total number of coins. For example, so instead of this example, I'll consider the example in our currency. So let's see this. So our denomination of coins are 1, 2, 5, 10 and 50. So all these are the denomination of coin. And you are supposed to pay rupees 27 to a shopkeeper. Now, how will you select and which type of coins will you give such that you take the minimum number of coins? So suppose first and foremost, the first step is sort the coins in decreasing order. So decreasing order will be 50, 10, 5, 2, 1. What is the amount to be paid? The amount to be paid is 27. So we are supposed to create a table in such a way amount, and what is the change you are opting, and what is the final amount remaining. So first and foremost, our initial amount is 27. So for 27, can we give the coin 50? No. So I am opting for giving rupees 10. And what is the leftover amount? It is 17 rupees. Then the next thing is, I am suppose the amount remaining is 17. What is the biggest denomination that I can give? It is again 10. So 17 minus 10, which is 7. Now the leftover amount is 7. So for 7, what is the biggest denomination that can be given? 5. 7 minus 5, 2. And then again, the leftover amount is 2. I do have a denomination 2, so I'll select that, and then we have paid the entire amount using 2 10 rupees and 1 5 and 2. So this is the denomination, that is, this is the minimum number of coins paid. What did we use? We were using the method of greedy method, that is, we were making the best choice at each step. So with the same, we can see the algorithm for the same. We have the change denominations, and we have to arrange them in decreasing order. And then for I is equal to 1 to r, we are beginning that whatever our total amount is, add a coin with value and subtract it from the total amount. Okay. After that, the next topic is halting problem. So there are many unsolvable. So by till now we have seen all the problems which were searching, sorting, maximum element, and the change making problem. All these problems were solvable, that is, we were able to solve them. But suppose there are some problems which are unsolvable. What do you mean by unsolvable problems? Unsolvable problems are basically which cannot be solved by any procedure, which cannot be solved by any procedure. So halting problem is a problem which asks whether there is a procedure that takes as input a computer program, and input to the program is taken and determines whether the program will eventually stop. So basically what we are doing with halting problems is that we check whether there is a procedure or whether there is a problem which can be solved with the input or not. So over here, it asks whether there is a procedure that takes as input a computer program. So the input for halting problem is a program, and input to the program and determines whether that program will eventually stop. So we are trying to find whether this program will run into an infinite loop or not. So this problem was actually developed in the year 1936. So every time we wanted to test whether a program entered into an infinite loop or not. Okay, so this, if we know whether a program enters into an infinite loop, it will be helpful in debugging. So first and foremost, checking whether the program enters into an infinite loop. Program enters into infinite loop. Why this is helpful? It is helpful when writing the program, and also when you are trying to debug the program. That is, when you are trying to take out the errors of the program. So we most of the computer scientists and mathematicians were trying to check whether such program exists. In 1936, a mathematician by the name of Alan Turing showed that no such kind of method exists. We cannot find that whether a program enters into an infinite loop or not. So this is known as Turing's proof that the halting problem is unsolvable. And what is the proof we are using? We will use proof by contradiction. Okay, what do you mean by proof by contradiction? That is, if we have a proposition P, we will take negation of P and show that this negation of P is true. Okay, proposition P is true and negation of P is true. It means both of them cannot be true at the same time. So this is known as proof by contradiction. So before we present this halting problem, first we have to understand that whenever we are simply running a program and observing it, we cannot determine whether the program runs into an infinite loop or not. Okay, now in this case, the proof is that we assume there is a solution to the halting problem. So our proposition P was a halting problem is unsolvable. So here we are considering a solution to the halting problem, which is a procedure called H of Pi. Now the H of Pi, what do you mean by these P and I? These two are inputs, one of which is a program P and the other I is an input to the program P. So both of them are inputs to halting problem. I is the input to the program P. Now it generates the string halt if H determines that P stops when given I as an input. Whenever you are giving I as an input to P and P is stopping, that means the input is valid and the program is halting or stopping. Otherwise, when the input is invalid, we will get the output loops forever. That is, our program is not stopping and it is giving loops forever as an output. For this, we have to derive a contradiction. So whenever a procedure is coded, it is expressed as a string of characters. So whenever our program is written, it is written in zeros and ones. And this string can be interpreted as a sequence of bits. So therefore, whenever we are taking a program, both P and the input should be able to determine whether it will halt or not. So for this, to show that no procedure H exists that solves the halting problem, we construct a simple procedure K of P. And what are we doing? We are considering that the same program P is an input to itself. So if the output is loops forever, it means K of P halts. And if the output is halt, that means it actually loops forever. So that is basically we are using proof by contradiction. Okay. Now this can be even explained by an example. We are taking an input program P. To the program, we are giving I as an input and we are getting the output, which is H of P. To this H of P again, we are giving an input program, the same program P. If it halts, if the output is halts, then it means our program is looping forever, and the vice versa, that is in the opposite case, if it is looping forever, is the output, then our program is halting. So both of these are the opposite things. That is, we are saying P is true and negation P is also true. So this is proof by contradiction. Okay. So this concludes the topic algorithm. Thank you.